Okay. All right, there we go. There we go. All right, there we go. All righty. All righty. Oh wait, I did that last time. That's true. Hello, everybody. Hello. I think I did this last time here. Hey, Planet, how are you? Okay. Who is I'm doing? I'm doing me. That's who's I'm doing. I'm doing very well, my friend. How are you? Are you how'd you did you have a good weekend? I guess I should ask. I think 99% of people who can't speak proper English would agree with you on that. Okay, that's fair. I gotta torture people every once in a while. That's how it has to roll, you know. Hmm. The right things must be done. What is this option here? Oh, okay. It's doing a BIOS setup there. Got it. All right. We'll wait a couple minutes here, and then we'll get started. Give me just a second here. do you find the rational zeros? The ones with the I at the end? Well, first of all, the ones at the I at the end, the imaginary zeros, are not rational zeros. So what you have to do first, Planet, is you have to find the rational zeros first, do the synthetic division to take out those two rational zeros, and then probably at the end of the problem, you're going to get a quadratic. If you say have 4 zeros, you take out 2 rational zeros. And then you could use the quadratic formula to find the 2 other zeros that have an I in it at the end. Otherwise, if they provide to you a complex zero, then its conjugate is also a zero, and then you can do synthetic division with that and see what your remaining polynomial is going to be, and then either use the quadratic formula or factoring or something like that to find your other zeros. So just depends what information that you're given there. But yeah, you always do you always start with the rational zeros test first if they just give you a polynomial outright. Yeah, so again, do rational zeros test first. Find rational zeros from the possible list. Do synthetic division. Hey, Gerda, how are you? Are you doing well? See a lot of people. Very good, very good. I hope your weekend was well there. All right. I think we got enough people in here. Sunday was kind of lame. Meh. Was that because you're a Packers fan there? I mean, you know, I don't know if you watch football or not. Okay. I just had to ask. Some people are very passionate about their football. So I am. I love the Bears. So I'm probably be a Bear. I'll be a Bears fan for life, regardless of how good or bad they do. All right. Oh, okay, I got you. Fair enough. Okay. All right. All right. Let's go ahead and get going here. All right. Hey. Yes, I did. So I sent you. I basically will take a look at it, and I gave you some feedback at the end of class. So there are a couple things that I saw in what you gave me there, Chase, that I can give you proper feedback for. So I looked at it like not 10 minutes ago. So I'll certainly give you proper feedback like you requested. All right. Okay, we'll go ahead and get going here. All right. Okay, let's get started today. Welcome back to Tuesday. All right, hopefully they were a nice weekend. All right, so today we're going to continue moving on here in chapter 4. Last time we talked about exponentials and logarithms. Okay, and we wanted to talk about characteristics of exponentials and logarithms, and we took a look at some examples in regards to that. So we looked at, say, properties of logarithms. We saw how to graph logarithms, again, going backwards from y to x in those cases. All right, today we're going to still talk about logarithms, at least to start with. We're going to talk about more properties of logarithms. These are particular algebraic kind of rules for logarithms that we're going to be exploring in here. All right, so we're going to see other ways to kind of either take apart or put together types of questions here for this particular guy. So let's go ahead and take a look here at question number 1 that you see up there. Go ahead and zoom in on that a little bit. There we go. Okay, so the first one says, what is the product rule for logarithms? So we're going to talk about these first 3 rules here. These are the 3 major logarithmic rules that we're going to kind of revolve around here. Let me bring up this guy. Okay. So let's bring up the quotient rule, the product rule, sorry, for logarithms. So that basically says this. It says if we have, say, log base b, say we have log base b of m, let's say m, and let's say we're going ahead and adding this. So we're add this to log base b of n. So let's say capital N. Okay, then what you can do is, what a particular property is that this can equal to 1 log in particular, so you can shrink from, hey JTS, what's going on, bro? So this is where you have log base b of mn. Okay, so you actually will get, like, again, this is why they call it the product rule, where addition is equivalent to multiplication between the 2 things on the inside of the logs. So that is basically what we have here for the product rule of logarithms. All right, let's talk about the, oh, it's all good, buddy. It's all good. I understand you were giving me an eBay rating, okay? I totally appreciate it very much. All right, so the next one here is, did I happen to read your email? When did you send your email there? Last night? Yeah, we could talk. You send me a whisper about what your email was about. I got like a ton of emails, so. Okay, so if we have log base b of m minus log base b of n, then we can also combine that into 1 log. That's going to be, again, the other way here, log base b of m divided by n. Okay, so that's what we have here for the quotient rule of logarithms. All right, so there's our quotient rule of logarithms. And then finally, we have one more rule of logarithms that we need to go over here, which is the power rule for logarithms. Okay, so let's take a look at that. So that basically says this. This says basically log base b of x to the r. So let's say we have a power like this, where we have log base b of x to the r, like so. What you can do with the power here in this particular instance is take the r and bring it to the outside here all the way to the left. So you can have r times log base b of x. So you can actually effectively just take away the exponent and bring it out to the left just like so. So that is the power rule for logarithms. So for the first set of examples that we're going to be doing here in this section, we're going to be using these three rules here in order to either compress or expand particular logarithmic expressions. Okay, so let's go ahead and do that right now. So let's do some examples, okay? All right. All right. So let's do some examples here, and we'll see what happens. Okay. Okay. So log base 5 of 125 over y. Now, what's our goal here in this problem? The goal is to expand this out as far as possible. So we have a single expression here. So the goal here is to expand as much as possible. And we'll also simplify as well. Okay, so let's take a look at our rules here. All right, so we have log base 5 of 125 over y. So let's go back to our rules in this case. All right, so I'm gonna put this on half a screen here. Put this on the other half. Okay, so looking at this here, what rule can we use here in order to expand this out? What rule can we use here to expand this out? So which rule should I use? 1, 2, or 3? So let's ask that question here. All right, 2 maybe. All right. The quotient rule. Okay, good. Remember, everybody, this also works backwards here as well. So let me at least show this off here. Remember, this works backwards, not just from left to right, but from right to left. But if it helps you see things a bit easier, I'll write it like this as well. Good. I'll show this off here. Sometimes it's just seeing things from left to right that people are pretty used to, but you know, it just depends. So, yeah. I'm just going to rewrite it in reverse here, so for you guys. Oop. Okay. And this one here is like this. Okay, there we go. All right, so I've written it both ways, so that way you guys can see. which one would be a little bit more obvious to use. And as you can see here in this case, we want to use the quotient rule here. So if we're going to use the quotient rule here in this particular instance, okay, then as you see how it works, we're going to keep the same log base. It's log base 5. So we're going to have log base 5, and we take that first number up top, which is 125, minus log base 5 of y. Okay? So that's what we have here in this case. Now, remember that you do have to simplify here. And as it turns out, log base 5 of 125 does have an answer. So let's go think back to what we talked about last week here. Remember how we solve for logarithms, okay? Again, log base 5 is not on a standard calculator. That's okay, Gerda. That's okay, Gerda, I understand. All right, totally understandable. Again, that's why I put up the replays there. So what is log base 5 of 125? What is log base 5 of 125? What's that going to be? So remember how we interpreted it last time, just to give you a friendly reminder here. Let's say, that's pretty bad. Let's say we have y is equal to, again, log base 5 of 125. Then we interpret that as 5 to the y power is equal to 125. That's how we convert it into an exponential. All right, so can anybody tell me what would y be here in this case? 5 to what power is 125? Three. Okay, 3 is correct. Okay, so 5 to the third power is equal to log base 5 of 125. So our final result here is going to be log base 5, 3 minus log base 5 of y. Okay, any questions about that so far? We're going to do a few more examples, of course. But now that you got a good idea about what some of these first problems are about, we're going to try a few more. Okay. Let's try this one. Okay, let's start off with log base 6 of x squared y. Log base 6 of x squared y. Okay, so what should I do here first? So what rule should we use here in this case? What rule should we use here in this case? Again, we could use a combination of rules here. Okay, the first rule there. Right, expand using the product rule. Okay, good. So notice we have x squared and y here. Okay, so we're going to expand using that first and foremost. So we're going to have here log base 6 of x squared plus log base 6 of y. Okay, so that's what we have so far. That's again using this rule right here, the second type. Okay, so again, that's what we have there. Okay, and what can we do with this first log here? Here we have log base 6 of x squared. So what rule can we use there in that case? Which rule? The power rule. Very good. So we're going to take this 2 and bring it out to the left. So we're going to get 2 log base 6 of x. Again, that just takes that 2 and brings it out to the left. That's all it really does. Plus log base 6 of y. Okay. Any questions about that so far? Okay. Any questions so far? No? Okay. All right. Okay. Let's go ahead and try another example here. This one will be short. We'll just go with that, x plus 1. Okay, so here we have the natural log of the 7th root of x plus 1. So the natural log of the 7th root of x plus 1. So how can we do that here? What kind of rule do you think we should use? Let's this one here is a bit tricky, so that's okay if you don't get it right away. Okay, now I know this one is a bit tricky here, but remember, one of the things to do here, what's the trick behind this, is to rewrite this problem. So that's the trick here. The trick is to rewrite the problem. We can rewrite this problem like so. We can rewrite this problem as the natural log of x plus 1 to the 1/7th power. Again, the 1/7th power because it's the 7th root. Okay? So then what we could use after that is then use the power rule to take that 1/7th and bring it out to the left. So here you get a 7th times the natural log of x plus 1. And that's your final answer for this problem. So that one's a little short, but again, a little tricky because you have to remember that roots can be rewritten in terms of their index. So whatever this number is, this could be 3 third root, it would be 1/3. Okay, 4th root, 1/4, and so on and so forth. Questions about that one? Nope. Okay. Now I'm going to test you on this part here. Okay. So I'm going to bring out a challenge type of problem here. So let's see if you guys can get this one. So this one here is pretty challenging. So there's a reason why I do this one. So we get log base 5. Okay, so here we get x squared y, the cube root, log base 5 of the cube root of x squared y over 25, all within the same root there. So, uh, okay. Now I want you to take like a minute or two and give this one a try using the properties that you see up there. Again, what are we trying to do? We're trying to expand this logarithmic form to as many logs as possible using all the rules that you see up here. So go ahead and give that a go. I'll separate these out a little more. No, actually, that didn't work out as well as I thought. No. There, that's a bit better. Okay. 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 Once you we'll go over the answers here, the answer together, by the way. So okay. All right. So let's go ahead and see if we can solve this one here together. Okay, just using these rules that we have here. Okay, so the first thing that you should have done, hopefully you did this, is again to rewrite the problem here once again. So you have log base 5 of x squared y over 25 to the 1/3 power. Then we can use the power rule to take this 1/3 and bring it outside. So we'll have 1/3 log base 5 of x squared y over 25. Okay, now let's talk about what comes next. So what comes next here is probably the trickiest part of the problem here. So let's see if you guys got this. Again, this 1/3 is on the outside here, and we have x squared y over 25. Now we're going to go ahead and use the quotient rule for that. But this 1/3 here stays firmly outside, so we're going to put a little bracket around here. We're going to have, say, log base 5 of x squared y minus log base 5 of 25. Okay, we're just going to use our simple rules there, just like so. We can also split the first one apart here, again using the product rule. So we have log base 5 of x squared plus log base 5 of y. Okay, so we can close that off, minus log base 5 of 25. Okay, the next part here is just to go ahead and clean up a couple of things. We're going to clean up the x squared part and the log base 5 of 25. So we got 1/3. We got 2 log base 5 of x plus log base 5 of y. That brings that 2 to the outside there. And we also have log base 5 of 25, which is going to be 2. And then what we can finally do is just take that 1/3. We can apply it to everything if we want to. So an acceptable answer here would be, say, 2/3 log base 5 of x plus 1/3 log base 5 of y minus 2/3. And there we've expanded it all the way out as far as we can go. All right. Now, admittingly, that's a pretty tough problem. Okay, so if you didn't get that right away, I totally would understand. If you didn't get it at all, I totally understand too. It takes a little bit of time just to kind of get used to using the rules correctly, kind of one by one. But you can see how we just kind of did it one step at a time, just kind of starting to expand things apart. Are there any questions about this example? Maybe you're taking your time writing that down. Any questions at all? Or do you guys think you got it? All right. If there are no questions, I'll go ahead and move forward then with the next example. Okay. All right, so I'm going to go ahead and erase this example here. Okay, now let's take a look at the next example here. All right, and we'll see exactly how this one works. Just a placeholder, but no. Just depends when we get done, and then I'll place it like a week after. Okay, so the next example I want to kind of show off here is just to kind of do something a little more simplistic, maybe if you think so. So let's go ahead and look at the natural log of x plus natural log of 7. Now, if we take a look at here, what's our goal for these problems here? The goal is to basically combine into one log. Okay, we're going to using the rules, of course. Tis true. Um, okay, so let's look at our example here. We're trying to and combine this expression here, natural log of x plus natural log of 7. We're trying to combine that just into one log, and that's going to be our answer. So let's take a look here. Which one of these three rules, 1, 2, or 3, are we going to use to combine these two into one log? Are we using rule 1, rule 2, or rule 3? All right, we're going to use rule 1, okay? So we got addition here, so we're going to add here. So that means we're just going to multiply the x and the 7 here together. So we're going to get a simple answer here. We're going to keep the natural log, and we'll just multiply the 7 and the x. And this is our answer. That's it. Natural log of 7x. Okay, let's look at another one. How about, sure. Okay, so taking a look at this problem here, we want to obviously combine it into one log. All right, so can anybody tell me here, what would we do first in this problem? What do we do first in this problem? What should we do first in this problem? What do you think looks like a good idea? We have to use a rule. Which rule should we use? Don't worry, ladies and gentlemen. I can sit here all day because I do. 2? Okay. Technically, that's true, but do we want to use 2 yet? Take a look at what you have here on the outside here. You have an 8 and a 4. So we want to take care of those here first. So use rule 3. Okay, so the reason why it's not 2, as you thought there, Gerda, is because we need to take care of the powers here first, and then we'll have 2 expressions that look like this. And you're too scared, just answer stuff. Man, look, I'll be honest with you, like I know this, but again, the reason for participation in this class is for me to understand your thought process. That way I can correct the errors that you might be running into. If you don't tell me anything, then I just don't know, and then I'm not able to help you as much. So, I'm just doing that's why I ask so many questions and why I wait so long, because that's pretty much at the end of the day, I just want your participation and feedback so I know exactly what's going on with you so I can help you. There's nothing more complicated than that. Trust me, I'm not here to make you guys look bad. I'm not here to, call you out on blah, 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 this, that, and the other thing. I'm here just to help, all right? Because I want you to succeed as much as the next person. So I'm not, trust me, I'm not here to be your enemy. That's the last thing I want to be. All right, so if you see here, rule 3 is going to be our answer for this case. Again, we want to make sure we have an expression here and an expression here. But we can't use this rule with these numbers floating around to the left. That's why we have to use rule 3 here first. So we have natural log of x plus 9 to the 8th minus natural log of x to the 4th. Now I can agree with Gerda and say, okay, now I can use rule 2 because I got some random expression here and some random expression here subtracted from each other, and then I can go ahead and put those two together. So here I'm going to get natural log of x plus 9 to the 8th over x to the 4th. And this is our final answer, just like so. That's fine. If you need my guidance, that's okay. Look, it's better if you tell me that you don't know rather than just say nothing, because then I don't know. I can't read your minds. I'm not about to start charging you $5 a minute to be a psychic either. So I need you to tell me tell me if it's a little tough. I said that's fine. I'll guide you through the problem. That's what I do. Are there any questions about this problem here? Any questions at all? No? Okay. You don't really get rule 3? Okay, that's fair. Okay, so, oops, I didn't mean to do that. I meant to do this. Okay. So rule 3 basically states here, Gerda, that if we have an exponent out here, we could just go ahead and bring it off here to the left and just rewrite it as, say, again, it would look something akin to this. If you have, say, natural log of x to the 5th power, you can take that 5 and bring it out here to the left, And what you'll get here is 5 natural log of x. So this is a special property of just logs in general, is that because you can rewrite them as exponentials, you could do that here. So when solving, we start with rule 3, then 2, then 1. So I would say this, and that's a very good question. What I would say actually is may not be necessarily 3, 2, then 1, but I can say for a certainty here, that's not the one I wanted. I wanted to go back to this. Okay, so let me put a note with that because that's a fair question to acknowledge here. So note, if combining into 1 log, then do rule 3 first, and then use either rule 1 or rule 2 as necessary. The reason why I did rule 2 here in this particular circumstance planet was because of the fact that I had this minus sign here in the middle. So after I got the powers done, I still had this minus sign here in the middle. So that's why I went ahead and used rule number 2. If this had been a plus sign, then I would use rule number 1. Well, so it just depends on that sign in the middle once we consolidate down to, putting the powers in their respective places. Are there any other questions? I hope that made sense there, Planet. And Gerda. I hope that made sense. Did that make sense to you, Gerda? About how it works for rule number 3? Oh, okay. No problem, no problem. Planet, you're okay with that, or do you need me to explain a little more? We're gonna do another example, by the way. So okay, all right. Let's do some more examples here. Let's go ahead and get a little bit more comfortable with this idea. Okay. Okay. So let's clear this out. Okay. All right. So, let's do this next one here. Which one should we do? All right. So let's take it up 1 notch, just a little bit. Okay. Okay. So we have 3 natural log of x plus 5 natural log of y minus 6 natural log of z. Okay. All right. So what do you think we should do first here? Okay, agreed. Let's use rule 3. So if we use rule 3 here, what would be this first part here then? This would be natural log of what? X to the third, that's correct. All right, very nice, Gerda. That's right. We're going to keep the plus sign here. We haven't done anything with that yet. Again, just using one rule at a time. How about 5 natural log of y? What's that going to be? All right. Good. Natural log of y to the 5th. Keep that minus sign the same. And in the same vein here, we get natural log of z to the 6th. Okay. Okay, now let's go from left to right. Okay, so let's just do it one rule at a time. So if we're starting from the left here, natural log of x to the 3rd plus natural log of y to the 5th, what rule do we use in this case? Okay, so if we use rule number 1 with just this first part here, just that first part, what does that combine to? So using rule number 1 here, so let me scroll up to rule number 1. Go. So if we use rule number 1, what should that look like? All right, that's right. So we're gonna, if we are adding two things together, we smush them together and multiply. So we have natural log of x to the 3rd, y to the 5th. Still have that minus. Okay. And now let's go ahead and put it all together. We have a minus sign here in the middle. So what should our final answer be after putting this all together? What is our final answer here based on the rules that we'll use? Well, let's answer this question here. What rule are we going to use here with subtraction? Okay, that's pretty close, Gerda. That's pretty close. Almost. Rule 2 is correct, absolutely. Rule 2 is absolutely correct. But notice we're going to have one log at the end of the day. So we're going to have this expression, this would be like your m, and this would be like your n, if you want to kind of call it that. If that helps for you to label each one so you know where they need to go using your rule, then that's perfectly fine. So this actually is going to be, that's okay, that's not a problem. So this is x to the 3rd, y to the 5th, over z to the 6th. That's correct, yes. So not that extra ln at the bottom there. That was the only issue. Um, Otherwise, everything else was just fine. So we're just combining it all into one natural log at the end of the day. Okay. All right. Doesn't roll. Very good. Uh, the 6, Chase put a 6 on the outside. Well, I put the 6 here. Oh, you know what I think you were missing? You're missing this last part here. It was a 6 natural log of z, Chase. I think it was hidden by my glorious picture of my camera, which probably led to that. That's my bad. Not your fault, Chase. My camera hid the last part that you kind of needed there. Whoops. Yes, that's correct, Planet. Yes. So first use rule 3, and then you can use rule 1 and rule 2 going left to right as it's necessary. Yeah, that's my bad, Chase. That's my bad. That's on me, buddy. Okay. Alrighty. Let's go ahead and gotcha. Okay. So those are a few examples there of expanding and compacting, um, logs here using our rules. So we spent quite a bit of time on that, but there's a lot we do with these rules here, especially if you plan to go on to calculus, you'll still be using these rules later on. So it's definitely a thing. Okay, now there is one more question here on this handout that we do want to definitely go over here, and that talks about the change of base property with logarithms. So as we talked about last time, on your calculator typically, you only have two logs on your calculator. You have log, which is log base 10, and you have ln, which is natural log, which is log base e. And we did talk about that last time. I said, okay, those are the two ones that you can find on the calculator. So the question is that, if I asked you and I said, okay, hey, can you guys find me the solution to maybe a question that looks like this? So let's take a look at a question here, and let's say this is our example that we'll use. And I'm just going to make it up, and I'll say, all right, what is log base 7 of 19? Okay, so log base 7 of 19, just two random numbers, okay? Now, you could convert that into an exponential equation, and it would be like 7 to some power is 19. And, well, that's good, but it doesn't I don't really know any number off the top of my head. 7 to some power is equal to 19. I have no idea what that is off the top of my head, and neither does anybody else here. So I need to go ahead and put it into a different context here in order for me to actually solve this. And again, we're going to use the calculator in which to do so. Okay, so the change of base property works like this. If I encounter a problem like this, okay, let's go with, use our math type guy. So if I have here, if I have log base b of, let's say, m, I could use what's called a change of base. So I can do this. I can change this to log base a of m divided by log base a of b. So this is the generic form of the change of base formula. You can literally change it to any other log base that you want. But let's talk about the practical side of things, okay? Because there are only two practical sides that really matter, and those are the ones that are on your calculator, okay? So all we want to do here is, technically we could change it to any base, but the only two that we actually care about is log base 10, which is just log. So we could have something that looks akin to this. So, whoops, sorry. So it could be log base m over log base of b, or it could also look like this as well. Natural log of m over natural log of b. So that's another way that we can express this change of base formula here in the same vein. Okay, either way, you're going to end up with the same answer. So I'll show you for this particular example how it works, and it's very, very easy. Okay, so if I have log base 7 of 19, all I need to do is put in a calculator is log of 19 divided by log of 7. And I'm going to end up with some random decimal number here, but that'll be the accurate random decimal number. So I can definitely put log 19 in my calculator, and I can divide that by log of 7. And so what I get here is I get, what you should have is 1.517 314. Okay, as a decimal going out to that many places. If you try it the other way, if you try it as natural log of 19 divided by natural log of 7, sorry, not 4, then let's take a look at what that answer is going to be. So natural log of 19 divided by natural log of 7. And if you notice, you got the same exact answer as you got from before. So either way, you end up with the same result by using the correct change of base formula. So either use log or use natural log. It doesn't matter which one you choose. Either way, you'll still win because either way, you get the same answer. Any questions about that so far? Any questions about that? Nope. Okay. Nope. Okay. Good stuff. All right. Let's go ahead and do another example then. Really fast. How about log base of pi of 17? So log base of pi of 17. So question is, how can we rewrite that if we're trying to figure that out? Log base of pi of 17. How do we rewrite that? So how do we rewrite this problem here using the change of base formula? Okay, good. Log of 17 over log of pi. Nice. All right. Again, you could put natural log of 17 over natural log of pi. And then we just go ahead and just put that in the old calculadora. And so here we get, what do we get here? 0.61172. Okay. And that's it. That's all you have to do for those problems there. Really, it's not too hard once you get used to the thing. So, okay. Okay. Any questions about this section here? Any questions? All right. I'll take that as a no. All right. Nope. All right. So, all right. Let's look at the. Let's go ahead and go to the next section here. So that's on the other page. All right. So we go ahead and close this out. All right. Okay, so let's go ahead and move on here to section 4.4, where we are going to be talking just about one thing for the most part, and that is exponential and logarithmic equations. So we may get through, we're going to get through, we're going to get through part way through this section here. I don't expect to get full through this section just because there's a lot kind of going on in this section here. So we may, yeah, we may just yeah, it just may end up happening. Just depends. In any case, let's talk about some properties here, and let's talk about how we can solve exponential and logarithmic equations. Okay, so number one, what rules should you remember into solving exponential and logarithmic equations? Okay, so now there's going to be another rule that we're going to certainly employ here in this instance. Let's talk about those said rules here, and they apply to both an exponential and a logarithmic case. All right. So the first rule that we have to remember is if we have, say, let's see here, yeah. If we have a b to the m power, and you find that to be equal to b to the b to the n power, okay, so let's say you have this, all right, then what happens here is just a direct result of that. And let me shrink this down. Okay, there we go. So this will be basically m will equal n. So that's essentially what will work out, is that you can basically kind of cancel out the exponents, and then you could be like, all right, the exponents equal to each other. That's fine. Okay. So that part there, not too bad. It is what it is. All right. The same thing applies here for logarithms as well. So if we have here, if we have log base b of m equals log base b of n, all right, then m is equal to n. So same result here. So you can basically, once again, cancel out the logs. If you have the same log and you have some expression equal to another expression, that's perfectly fine. Also, a couple of other things to remember here is don't forget your log properties here. Okay, so let's put a note for some of these here. Note, do not forget your log properties or rules, okay, in order to manipulate exponential and logarithmic equations. Okay, so those log properties and rules we talked about in the previous two sections, yes, they're going to play a pretty big role in this section as well. Okay, we're going to be using those extensively as we try and solve for x in various circumstances. Okay, so let's take a look at how this works. All right. So the way this works is, let's look at several examples. Okay, so we're going to do several examples here. This is primarily what we're going to be doing here the rest of the time. So um, again, just giving you a little bit of a heads up. Okay. So Let's do the first one. All right, so let's start off with something easy and let's kind of work our way up, okay? And we'll start off with something easy and work our way up. Okay, so let's start off with a 3 to the x here is equal to 81. So here's a simple exponential type of problem. So 3 to the x is equal to 81. All right. So what is x going to be here? 3 to what power is equal to 81? 3 to what power is equal to 81? All right, x is equal to 4. That's correct. All right. Now, if you didn't have a table of powers or whatever, let's say 3 to the 4th power or something like that, what's another way to kind of do this problem here? Using the kind of little rules to remember here about our properties that we just kind of talked about here. Well, one of the things that can be very helpful here is putting this in the same same base. So, um, for exponential equations, try putting both sides using the same base. Okay, so 3 to the x is something, but we can rewrite 81 as 3 to the 4th power. So what you do know is that since you have the same base here, then that would just imply that x is equal to 4. Okay, so if we can put it in the same base. Now, of course, that's not always possible, but again, if we can, then we can rewrite it just like so, and we could get a nice easy answer out of it. Okay, let's try another one here though. Sure. Let's try this one here. So we'll crank it up a little bit. So we got 9 to the x power is equal to 27. 9 to the x power is equal to 27. Now, they look pretty similar in some respects, but can we express this using the same base? Can we express this problem here using the same base? What's another way to say write 9, for example? We can write it as some number to some power. What's another way to write 9, for example? Okay, let's use 3. Okay, so 3 to what power is, oops, I mean, 3 to what power is 9? 2. So 3 squared is equal to 9, and then we have an x here on the outside. We have 27. That also could be rewritten as 3 to what power? Okay, 3 squared, right? So 27 can be rewritten as 3 to what power is 27? All right, 3. That's correct. So let's take a look at what happens here. Here we have 3 to the 2x power. Again, using rules of exponents, we just multiply those exponents together just like so. This is equal to 3 to the third power. So in effect, again, you can cancel these 3's out if you want, and therefore you're left with 2x is equal to 3. So x is equal to 3 halves. And that's your final answer for this problem. All right. So you can see we put it using the same base, and we got that down. And there you go. Easy peasy, lemon squeezy, at least so far anyway. I'm going to look at a few more here for sure. Because some of these problems, I will admit, can be rather tricky, so I'll have to pay attention a little carefully here. All right, let's look at the next one. All right. Okay. 5 to the 2 minus x power is equal to 1 over 125. Okay. Now, if you see there on the left, we have a 5 to some odd power. Again, a 2 minus x power. What about the right? How can we rewrite 1 over 125? Actually, let's do this a bit easier. What's another way we can write 125, at least to start with? So what does that kind of convert to here? 5 to the third, okay. So I can rewrite this as 1 over 5 to the third, all right? So that's 125. Okay, but 1 over 5 to the third can be rewritten as one other expression. How can that be rewritten? What's 1 over 5 to the third power? What was that again? Oh, that's pretty close, Gerda. Not quite, though. That would be representative of the cube root of x. Or cube root of 5, I should say, sorry. So we talked about this rule quite a while ago, but this is a very important exponential rule that we're going to use here. Anybody remember what that was? No? Okay. So if you remember this, remember 1 over a to the n power here is equal to a to the minus n power. Remember, that's what we talked about here. We talked about exponents. We said, okay, negative exponents is definitely a thing. Well, there you go. We've definitely made it a thing. So here we get, again, yeah, 1 over a to the minus n is a to the n. All right, so if again, we move from numerator to denominator, or denominator to numerator, to change this to 5 to the minus third power. Okay, so this is kind of a very important example just to highlight that one little factoid, that one little fact about exponential rules that you're going to have to remember, is that if you're trying to convert it, then this is what we'll need to do here in order to get the same base to come with us. So we're going to have 5 to the 2 minus x is equal to 5 to the minus 3. Okay? So again, these 5's here, they'll cancel out. And then all you're left with is 2 minus x equals negative 3. And so all we do here is subtract 2. get negative x equals negative 5, divide by negative 1. And so here we get our final answer here of x is equal to 5. So x is equal to 5 for this problem. All right. So don't forget these important rules here for negative exponents. And it's still going to play a factor. All the rules of exponents will still certainly play a factor into determining what some of these problems are going to be. Okay. Any questions about that problem? No? Okay. All right. Let's do the next problem then. Could we just subtract the exponents in the original problem? Are you talking about this? Let me see if I understand that right, Chase. So what you're saying is that, are you saying that this would be equivalent to 5 to the 2, like minus 5 to the x? Is that what you're implying there? I just want to see that if that's what you're talking about, or are you talking about like doing this? If this isn't it, then is this it? Then are you doing like let me see if I got this right. Like this. Like something akin to this? Is that what you're talking about, Chase? I just want to know which way we doing subtracting the exponents there. Yeah, so I mean, you could do that there, right? And that's perfectly fine, right? But not every problem is going to end up to be necessarily that way. This is a good way to just kind of highlight kind of how we can justify that answer, because not every problem is going to be as straightforward as this. Actually, to kind of acknowledge your question a little further, let's do the next example I have in mind. And you'll see why I don't like necessarily doing that in every single case. Okay. Okay. So this is our next problem here. 8 to the x plus 3 equals 16 to the x minus 1. All right. So the question is, can we put these either side using the same base? That's certainly plausible, yes? Absolutely. We could have radicals in these equations, sure. No, that's not a dumb question. It's a fair question because we had radicals in the last set of equations in the last section. So it makes perfect sense to ask that question. And the answer is yes, it's possible to have radicals in the equation, yeah. So what base can we set these both equal to? I'm going to make a contention here that we can put 8 to the 8x plus 3 and 16 to the x minus 1 power, that we can use the same base here for both sides. What base can we use? Think of another way to write 8 or another way to write 16. 2. That's correct. Very good. That's right. So we can rewrite 8 as 2 to the third power, and we have x plus 3 here. And 16 can be rewritten as 2 to the fourth power, and we have an x minus 1 there. Now, we have the same base here of 2, so effectively we can kind of, again, cancel out the 2's here. We're left with 3 times x plus 3 equals 4 times x minus 1. And we just go ahead and proceed to solve for x. So you get 3x plus 9 equals 4x minus 4. Subtract 3x. This is a little small, but it is what it is. Add 4. And so here we get 13 is equal to x. Okay. And that's our final answer for that problem. All right, good stuff. Any questions here so far? So that's kind of like the last of the basic questions. Now we're going to go on to the more complicated questions. Yeah. All right. Let's look at the next question here. And this one here is going to be slightly a bit more complicated. So let's talk about how we can do this next problem. All right. So let's start off with something a little simple, but a little complicated at the same time. So let's try. So here's our first example. 5 to the x is equal to 17. Now, unlike what we did for the last few examples, we do not, unfortunately, have anything that reflects 5 to some nice power equaling 17. That's just not a thing. However, in order for us to go ahead and solve for these problems here, let's talk about the trick behind these problems here specifically. So the trick here behind these problems is to use log properties or rules, okay, to get the exponent by itself, okay? Now, the question is, it's like saying, okay, well, how do I do that? Well, yeah, there's a definite way of which to do so. So the log property that I'm going to use here in this instance, so I can tell you how to do this problem, is I'm going to take the natural log of both sides. Okay, so I'm going to take the natural log of the left side and the natural log of the right side. Again, in algebra, everything is a balance, so if I do it on one side, I can do it on another side. Okay, so now that I have that, I am now free to go ahead and use those log properties in order to simplify this down further. Notice that we have an exponent here of x. So what we'll do next here is we're going to bring that x out to the left. Remember, using our power rule that we just talked about in the last section. So we have x times natural log of 5 equals natural log of 17. Okay, so now we got x natural log of 5 equals natural log of 17. Okay, so what should I do next? How do I solve for x? What do you think I should do next here? What should I do next to solve for x? This is actually one of the most important questions here because it's usually the most confusing part. So you use your exponent rules, you use your log properties, okay? Okay, that's correct, Planet. That is absolutely correct. Very nice. Very nicely done. So what we do here specifically is we go ahead and divide by the natural log of 5 on both sides. Again, this is important because I want you to understand that natural log of 5 is just some random decimal number, okay? I don't know what natural log of 5 is off the top of my head, but what I do know is it's like a number. So it's like if I had, say, 3x equals 10, well, you just divide by 3 on both sides because 3 is just a number. Well, I'm not doing anything different here when I go ahead and evaluate something out for x. So here I have natural log of 17 divided by natural log of 5. I bit bop boop that on the calculator, and then I'm going to end up with an answer here. So I get natural log of 17 divided by natural log of 5. And so I get, what do I get here? 1.76, this is 0, 4. All right. All right, fine. Okay, so that's what I get here for this particular problem. All right, so again, make sure you have this correct here so that way you're using the calculator correctly. You're entering that in correctly. ln 17 divided by natural log of 5. You have that set and ready to go. Okay. Okay. Any questions? Hopefully that's not too bad. We're going to do another problem, of course. Let's just do it now. All right. Let's do this next one. All right. Next one here is we're going to go ahead and do Okay, so this is the next one here. 5 to the x minus 3 is equal to 137. Okay. All right. Oops. Okay, so let's talk about what we're going to be doing here for this one. So in this one here, just again, remember the first step here. Okay, so the first step here is we're going to go ahead and take the natural log of both sides. Okay. All right. So that's what we're going to do here first. Take the natural log of both sides. So let's do it. So we'll take the natural log of both sides here. All right, so we have the natural log of 5 to the x minus 3 equals the natural log of 137. Now we're going to go ahead and take this x minus 3 here. That's a power. We're going to bring it out here to the left. So what we'll have next is we'll have x minus 3 times natural log of 5 equals natural log of 137. Okay. And then we just go ahead and do, you could do anything really here for the algebra stuff. So if say, hey, I want to solve for x, you could go ahead and divide by natural log of 5. Again, natural log of 5 is just a random number, or you can distribute whichever way you want. And so we have x minus 3 is equal to this expression here. And then we just add 3 to both sides, and we'll get our answer here for x. So now, I do want to point out one thing here, okay? One very, very important thing, all right? So this is a common mistake I see quite often, so I do want to make a note regarding this, okay? Um, so the most common mistake I see in these problems here specifically has stuff to do with this kind of last part that I often see. Natural log of 137 over natural log of 5. What people do on their calculators there is they'll put in natural log of 137 over 5, okay? So what they'll do is this, but this is definitely not the same as the natural log of 137 divided by the natural log of 5. These are not the same thing, okay? So these are not equal to each other. So do not enter this into the calculator. Don't do this. You want to do this. Want two separate natural logs here. So make sure not to make that mistake when you're trying to plug in numbers on your calculator there. So I'll go ahead and do this one out here. I'll add 3. Okay. So my answer for x here is going to be 6.057. 5657. Go 57. All right. Sure. Okay. Questions about that? Nope. All right. Okay. Now there's going to be definitely many more examples for us to do. This section has quite a few examples that we just kind of have to slug through. So this one here I know will take a little bit of time to kind of get through, but once we do, it'll be quick right after that. So what we're going to do here is we're going to go ahead and stop here for the day. Okay, so this is where we will stop. Okay, and we'll pick up with some other examples from this section for next time. Okay, so more to do here certainly for next time. All right. Yes. I forgot. One more announcement here. One more announcement, by the way. I did go ahead and extend the homework out to tomorrow. So the homework is available till tomorrow for you to do. Okay, so that is available till tomorrow. All right, so if there's a little bit of last little extra bits that you haven't finished for the homework, then it is available for you. All right. No problem. Okay, any questions, guys? No problem. All right, so that'll take care of it for today, everybody. Thank you very much. Thank you very much for coming out here today. I really appreciate the time and the energy it takes to come out to these lectures. I appreciate you all, and I will see you all here in a couple of days next time. Okay? All right, everybody, take care of yourselves, and I will see you later. Chase, I'm gonna go ahead and talk with you here a little bit afterwards. So stay with me. All right. Okay. Take care, everybody, and we'll talk to you later. All right. Bye, everybody. Have a good one, man. Okay, Chase. Chase. You there, buddy? Chase, you there, buddy? Okay, so I want to give you a little bit of feedback that you asked for. So if I were to kind of break down kind of what I saw there, there was a couple of things. It kind of looked like you weren't sure what kind of order to go in terms of rational zeros. So remember, you have to do you did kind of okay there, so which was all right. So you have to first of all, again, you have to find the possible rational zeros. Okay, first. Okay, then test on the calculator. Do synthetic division, and then use the quadratic formula um, to find the other two zeros if there are other two zeros. Okay, now one thing that I noticed here when you talked about the quadratic formula is that in one case, when you use the quadratic formula, you didn't use the plus minus sign in the middle. So it's, negative b plus or minus the square root of b squared minus 4ac. On your work, I saw that you were missing that on one of the first instances of you using the quadratic formula, which is probably why it didn't turn out so well, because you had something like negative 37, and then you had that times the square root of something, which probably messed you up a bit. So you're missing that plus or minus there. So be sure to, if it helps you, Chase, go ahead and write out the quadratic formula before you plop numbers in, so that way you can just reference back to it, just in case if you miss that part. The second part that you had a little bit off there was, again, you will need to go ahead and simplify what's inside the square root of the quadratic formula. So be sure to simplify that if it's possible. Now, the second part that you did for the quadratic formula, it was fine, but I didn't see any refinement necessarily. You didn't really add the 1 and the 20 there. So because you had the 1 and the 20, I was like, okay, why don't you put that together as the square root of 21? Now, if that's simplified with the over 10 part that you had there, well, then it was like, okay, well, you could have possibly reduced that down. Now, in that case, it doesn't, mind you. That doesn't reduce it down, but it could possibly, if it happened to be like, say, the square root of 4, and then that reduces to 2, and then, of course, now it can simplify after that. So, thing is that you just have to be careful about that. Make sure to simplify what's inside the square roots before you go ahead and put that answer together. So again, you remember, one of the things that I suggested is, split it up into two fractions. Okay, so split it up into two fractions. So that's another thing that I suggest, i.e., you had, say, negative 1 plus or minus the square root of 21 over 10. That would be like negative 1 over 10 plus or minus the square root of 21 over 10. It would look something like that, like two separate fractions, just in case if you had to simplify one of the fractions but not the other. Something like that can happen as well. So that was kind of like the major things that I saw. I saw you mostly you mostly did pretty well on the first parts. It was just that last little bit with the quadratic formula there. You make sure you have your equation right, and then you could put 2 and 2 together after that. And you should be able to get that without too much trouble. Yeah, I know it's small little things, but as you know, in math at least, it's one of those cascading things that if you get it wrong, then it cascades all the way down to the end of the problem. So, yeah, I just want to be make you aware about that, so that way, you just kind of have to be a little bit more detailed there. So, based on what you just showed me, yeah, that's just kind of like the feedback I got for you. You got any other questions there for me? The sponsorship. So, you should tell me what's this I'm a little confused. What is the sponsorship about? Um is it me like being like an academic advisor or something like that? I don't know what that's about. I saw that other email. I was like, okay, what's going on there? So fill me in, my friend. Fill me in. Okay. Mhm. Okay. All right. Okay. Hello. Okay. Extravagant club. I'd be part of the group and activities. You just need to fill out some paperwork from the school. You'll probably get funding for the equipment. Okay, I mean if it helps. If it helps you start the club, I'm not sure how obviously I'm not sure if I could be part of the activities or the group because I'm pretty busy. But I don't mind if I sponsor you. Sure. I'm down with that. Send me the paperwork about where I need to kind of fill out stuff, and then I can send it back or at least forward it over to who needs to get it. So I don't mind helping you and just say, hey, I'll sponsor this club and dot dot dot. Sure. If I have to come to campus, it's not a big deal. So basically, here's what I would like you to do, Chase, okay? Just send me an email in regards to what I'll need to do if I can sponsor. The only thing I'm not sure about, and something that you may want to ask about, is if an adjunct faculty, yeah, just ask one thing: if an adjunct faculty can sponsor your club. So if an adjunct faculty can sponsor your club, I'm good to go. If they can't, well then, yeah, you're gonna have to find a full-time faculty then. So I don't personally know the rules on clubs, so just ask about that. If I'm good to go, send me the paperwork. We're good to go, bro. Okay? Okay. Got that info by tomorrow? All right? Just let me know via email, all right? Okay. I'm not sure either, but I just want to follow the rules, that's all. I honestly don't think it'll make a difference, but still, you know, just saying. Okay, Chase, you have a great day, all right? I will see you in a couple days, my friend. Talk to you later, my friend. All right? Have a great one. All right, see ya. All right. Bye.